Hi, my name is Wagner Kamakura, and in this tutorial, I'm going to show you how my predictive stepwise linear regression works. You probably have already seen enough of linear regression and stepwise linear regression because those topics are covered either on a stat class in college or in a data analysis course in graduate school. But I'm going to give you a brief review of stepwise linear regression. In case you want more information, you can look at my tutorial, which you can search on YouTube with the title Stepwise Linear Regression for Excel, or you can try this link. So let me give you a very quick idea of the standard stepwise linear regression. And I'm going to explain how the forward stepwise process works, which is the most commonly used. The first thing that stepwise linear regression does is to select a predictor that shows the strongest correlation with the dependent variable and run the first linear regression. So it's going to find out the predictor among the candidates that has the highest correlation with the dependent variable and will run that linear regression. Then it will add that first predictor into the linear regression and then run one linear regression, adding each one of the remaining predictor candidates to the first predictor. And after running each one of those linear regressions with the previous model and adding one of the remaining predictor candidate, stepwise linear regression will select the predictor that shows the highest increment in fit relative to the current linear regression model and shows a statistically significant increment in fit. In other words, it first does a statistical test to see whether the increment in fit, because there's always going to be some increment in fit, because as you add more predictors, your R squared cannot go down. It has to either remain the same or go up. The question that stepwise linear regression answers is, can we expect that this improvement in fit will happen in other data sets? And so it does a statistical test. If none of the predictor candidates produces a statistically significant increment in fit, that means you already have the best possible model. Stops. Otherwise, it will add the best predictor, the one that produced the highest increment in fit and is statistically significant, to the model, and repeat steps 2 and 3 until it cannot improve anymore. You cannot find any statistically significant improvement in fit. So that's how stepwise linear regression works. If you look at the process, it seems very clever and it appears to be very effective in selecting predictors, especially when you have a large number of candidates. However, this process, this stepwise linear regression process, has many potential flaws, especially for big data, either when you have a large number of predictor candidates and or when you have a lot of observations. The main problem with stepwise linear regression is the fact that it relies on a statistical test for fit. It's called the F ratio or the F test. And the problem there is that the F test is designed for a single test. You're testing whether this model produces statistically significant improvement in fit or not. So it's a test designed for a single test. But in the stepwise linear regression, the test is used sequentially, testing multiple predictors in sequence. And because of that, because the test was designed for a single test, but in stepwise is used sequentially, it leads to overfitting. The p-value, statistical significance, looks smaller than they actually are. And the confidence intervals for the regression coefficients tend to be smaller than they actually should be. So the confidence intervals are overly confident. And that leads to overfitting. In other words, it leads to a model that fits well, explains well the calibration data, but might not be the best model to make predictions out of sample. And that problem also becomes larger, becomes more prevalent, not only when you have more predictors, but also when you have more observations. So if you have a larger sample size, the larger the sample size grows, the more likely it is that the model will be overfitting the data. Of course, we can try to fix this problem by changing the criteria for including or dropping predictor. Only include a predictor if the p-values are very small. but how you're going to figure out the proper p-value. So in general, stepwise linear regression has this problem of overfitting, which is not a major problem if you're trying to explain your observations, but it's definitely a problem if you're trying to use a model later on to make predictions. Because we know that models that overfit, that fit too well to the observed data, might be actually fitting over random error. And that random error is not going to be the same that you're going to observe when making true predictions. So if you're going to make predictions, you want a model that does not overfit the data. And again, this is the problem, is that selecting predictors based on fit, even if you use a statistical test, fit in a calibration sample, emphasizes the exponential known data. But we often use linear regression models to make predictions of an unknown dependent variable, unknown values of a dependent variable based on known predictors. So we want to know how well the model will perform on future unseen data rather than on the observed data that we use for calibration. And that's where my predictive stepwise linear regression comes in. The very simple idea that I have to admit is not being thoroughly tested, but is based on the same principles used in machine learning, the idea of cross-validation, of assessing models not on the calibration sample, but on a holdout sample. So the main idea is to select predictors based on predictive performance, on how well the model predicts the dependent variable on a holdout sample, rather than based on fit, calibration sample. Contrary to the standard stepwise linear regression, we are going to select predictors based on true predictive performance, performance on holdout data, holdout sample that we did not touch. And the idea here, the goal here, is to build a model likely to perform well in predicting the unknown dependent variable, rather than explaining the data that we already know, the calibration sample. First step is to randomly split the sample into p proportion holdout cases and the remainder keeping the calibration sample. So we're going to split our data into a holdout sample and a calibration sample, and that is done randomly. Then we run one linear regression on the calibration sample, adding each one of the predictor candidates to the regression model. At the very beginning, we run one linear regression using each one of the predictors calibrated in the calibration sample. Then we apply the calibration regression coefficients to the selected predictors in the holdout sample to make predictions of the dependent variable to calculate the prediction error. And then we compare the sum of squared prediction errors obtained with the inclusion of each one of the predictor candidates with the sum of squared errors of the current model. So we had the previous model, added one predictor at a time to the current model, calibrate in the calibration sample, then we use the model to make predictions in the holdout sample. And the criteria to select a predictor is the performance in the holdout sample. If none of the predictor candidates produce a reduction in sum of squared errors in the holdout sample, we stop. That means that we cannot find a better model than the current one. We cannot add more predictors to it. Otherwise, we add the predictor candidate that produces the largest reduction in sum of squared error in the holdout sample. And keep repeating steps 1 through 4 until we cannot reduce sum of squared errors in the holdout sample. Let me show graphically how this works. So here we have the sample, and we randomly split the sample into p proportion of holdout cases and 1 minus p calibration cases. And we calibrate the regression model in the calibration sample, get the regression coefficients, apply these regression coefficients to the holdout sample, and calculate the prediction error in the holdout sample. And we do this by adding each candidate predictor at a time to find which predictor candidate would produce the lowest prediction error, and also to determine whether adding any one of those predictors to the current model will reduce the prediction error. If it doesn't reduce the prediction error, we already have the right model. Not the right model, but we cannot improve on it. If there is a reduction in prediction error, we pick the candidate predictor that produces the largest reduction in prediction error. And you keep doing this for each one of the candidate predictors to select the next predictor to enter the linear regression. Then now this becomes the current model. Repeat the process again to find what is the next predictor to include until the criteria does not improve, until we cannot reduce the sum of squared errors. At that point, we have the best possible model. Now, to improve the performance of this predictor selection process, we replicate this process k times. Instead of doing this only once, we draw, let's say, k equal to 10. 10 random samples from our original sample. Perform this split into holdout and calibration 10 times. And at each stage, we select the predictor that produces the largest reduction in prediction error across all 10 replications. So again, the idea here is we randomly split the sample into holdout and calibration, then run one linear regression on the calibration sample, adding one predictor at a time to the regression model. Apply the calibrated regression coefficients to the select predictors in the holdout sample and calculate the prediction error. Compare the sum of squared prediction errors of the new model, current model plus the new predictor candidate. With the current model, if there is no improvement, you cannot produce a reduction in sum of squared errors with any of the candidate predictors. We already got the best possible model. If not, we now add the predictor candidate that produces the largest reduction in sum of squared prediction errors. And keep repeating and do this k times and repeat this process from steps 1 to 4 until the process cannot find any additional predictor. And that's pretty much how the predictive stepwise linear regression model works. Now I'm going to show you how you can run this automatically using my analytical tools for Excel, Kate. For this demonstration, I'm going to use an example you can find in my Kate, Kamakura Analytic Tools for Excel. There is a spreadsheet there that contains multiple examples. And if you navigate through the tabs, you're going to find a tab with a sample data set for predictive stepwise linear regression. And in this example, each row is data for one used Audi advertised in classified ads in Europe. For example, the first row here, it's a fairly expensive used Audi, 65,000 euros, with about 29,000 miles, manufactured in 2015, with 2,900 cc's of engine displacement, 200 horsepower, etc., etc. What we are trying to do here is to run a hedonic price regression, a regression where the dependent variable is the price of the product and the predictors will be a collection of descriptors of the product. And we are going to try to do this using a stepwise linear regression, but one that is geared towards prediction rather than fit. If you go to add-ins, before I get to that, you can see here a very brief description of this particular tool and how the data has to be configured. All my tools are very finicky about how the data has to be formatted. Assuming that if you're using these tools, you are very well versed in Excel, so you can always transform your data into the format that is required by each one of the tools. I'm going to add-ins, Kamakura Analytic Tools, and here you have in the collection of regression models, predictive stepwise linear regression. It says that it runs a linear regression with cross-validated stepwise predictor selection. Maximum of 100,000 observations, rows, and 100 predictors, columns. It already picked the range of the data. If not, you have to specify where is your data. It says that it read 15,000 rows. There are 19 candidates for predictors. And here it says, do you want to keep the default parameters or you want to specify your own? I'm going to specify my own. Essentially, you need to specify only two things. What proportion of the sample of the 15,000 rows do you want to randomly select for holdout? I'm going to put 30%, 0.3. So it's going to randomly hold out 30% of the rows for holdout, for validation, and 70% of randomly selected rows for calibration. And by default, it's going to do this 10 times. Let's say I'm going to do this 5 times. In other words, it's going to run the cross-validation 5 times. And it's already doing it. It's following the process that I just described. And there we have. It shows the R square in the calibration, the fit of the model in the calibration sample, the R square on the holdout. So this is true predictive performance because it's how the calibrated model obtained in the calibration sample fit in the holdout sample. We held 30% of the sample as holdout. This is how the regression model was improved with the first, second, third predictors, the cumulative R square. And here are the regression coefficients. Why don't we have standard errors? I didn't put the standard errors because we did not select the predictors using sampling statistics. We did it using cross-validation. The purpose here is to make predictions, not to interpret the coefficients. And that's pretty much it. Very straightforward way of running stepwise regression with the goal of maximizing predictive validity, predictive fit.